definition of a rational function, r of x, it's some function, r standing for rational, is equal to n of x divided by d of x. It's the division of two functions. Very good. So this is true where d of x does not equal 0. Just based on the principle that we can't divide by 0, we get undefined, or we can't get an output with a 0 in our denominator. N of x and d of x are simply polynomials. I'll write shorthand polynomials. Part of your homework is going to be finding the domain of a rational function. Well, we know that finding domain, typically with functions, there's more inputs that give us outputs than inputs that don't give us outputs. We look for our restrictions. So what do we think the restrictions are going to be for a rational function since we're dividing two things? What can the denominator not equal? 0. So to find the domain of a function, you set the non-simplified form of d of x equal to 0. Sorry, you set the simplified form of r of x. The non-simplified form of r of x, you set d of x equal to 0. These are restrictions. This right here is the restrictions on the domain. And then we write on the domain. And then we simply write the domain in interval notation. Okay, first one, determine the domain of the given function. Do we have to concern ourselves with the numerator? No. Now, if you look there, the numerator is probably factorable and the denominator is factorable. So we could factor them into two binomials and they could cancel in some capacity. Let's simplify the rational function. But do we want to do that process for the domain? No, we don't. We simply set the denominator equal to 0, which is x squared plus 5x minus 6, correct? Set it equal to 0, and whatever the solutions are, the restrictions on our domain, MAG, do we agree? Multiplies to be negative 6, adds to be 5. We have 6 and negative 1. All right, so now we have x plus 6, x minus 1 equals 0. And when we solve, what do we get? Negative 6 and positive 1. These are our restrictions on our domain. So our domain is, and you could just write interval. You don't have to write d with the colon. You can just write the interval. It'll be negative infinity to negative 6. Parenthesis, remember, because negative 6 is not a part of the domain, right? Union, negative 6 to 1. Union, 1 to infinity. Next part of the notes is what is called determining limits of a rational function. Within mathematics, now that we have functions that don't have outputs, what we do is we calculate, or we do this process called determining limits. Meaning, what is the function limited to, or what are our outputs limited to? This is the next part of the notes, correct? Yeah. Okay. So, the two types of notations that you will see, I believe in the book, the second one is the way it's written. Yeah, I know for sure. The second is how it's written, but it also may be written like this. LIM stands for limit, and it says x arrow a, which means as x goes to a, f of x value is going to what? Another way they write it in the book is as x approaches a, f of x or our y value equals. That doesn't mean what is our y value equal, it means what is it going to. So look at the verbalization of this. As x approaches a, and it's going to be some specific value, y, or f of x, remember f of x is our output, which is a y, is approaching blank. And that's what you're going to fill in, this blank here. Okay? Altogether, you're going to have two limit statements like this one or that one, for every asymptote. That will make sense as we go through. Now, note, I don't think you have to create the limit statements all together. You simply have to fill in this blank, okay, which is kind of nice. All right, so let's look at this graph here. First, we have 3 parts of the graph. Now, what we do is we want to go to the extreme of the graph. So let's say that we're this black dot here. We're just a little ant walking on this curved road, and we have 2 directions we could go. What's the 2 directions? To the left, correct? But it's going to the left, and also what is it doing? Going down. So that ant could go to the left, or it could go to the right, correct? So for each direction that ant is walking on the graph, we have a limit statement. We're going to write it in this fashion so we get used to the notation within the book. As x approaches, when we move this way, there is a simultaneity here. You're moving to the left or right, and you're moving up or down. When we're moving in this, bless you, the direction right here, what are we moving, left or right? Left. And if we kept moving on left, what is x approaching? X is going to negative infinity. Very good. That part in your homework, they are going to give you, and you just have to fill in the blank. So as we move to the left, we're going down. But we have a horizontal asymptote. So what's going to happen to the graph? As we talked about, it's going to flatten out, correct? And it's going to get closer and closer, but never reach what value? 1. So as x goes to the negative infinity, the y value is getting closer and closer to, but never reaching 1. Remember, what f of x equals is not what it equals, but what it's approaching. If you thought of an input-output table, as x got very, very small, our y value would be 1.000001, really close to it. Got it? Okay, does this look familiar, yes or no? Yes? Okay. We'll do one more and then move on in the interest of time. Let's talk about the ant standing on this graph, moving in this direction. Okay? The ant standing on this graph and moving in this direction. We have 2 things that are happening. X is moving left or right. Is the first one. If we're moving this way, what is it moving, left or right? Right. And what x value is it getting closer and closer to? But we see it's never going to reach 1. So it's getting closer and closer to the x value of 1. Comma. F of x. What is, now it's moving to the right, but now in terms of up and down, what is it doing? It's going down and down and down, correct? And it will never reach this asymptote, but in terms of the y value, it's going down without bound, which means it's going to what? Negative infinity. Now, if we look at this, we're not going to write another limit statement. You could. If you notice, we have 1, 2, 3, 4, 5, 6 limit statements that we could do, but I'm doing just a couple in the interest of time. This is saying as x approaches 1, f of x is going to negative infinity. But don't you agree we're going to have an ant that's going to be here that's going to be approaching the x value of 1 as well? So how do I know if this statement is talking about the ant right here in green or the ant walking on this red? Well, this one's, yes, going to negative infinity. But what if I didn't give you the graph and I just gave you this? How would you know what ant you're talking about? My point is this. What's different? Yeah, what's different about this ant down here versus this ant down here? What's relative about this ant relative to the asymptote? This ant is relative to the asymptote. It's to the left of it or the negative side of the asymptote. The right ant over here is to the right of it or the positive side of the asymptote. So if we're talking about this ant, the notation we use is a negative in the exponent of the 1. That's not the exponent. That's the notation to indicate we are approaching 1 from the negative side of the asymptote. What if we're approaching from the positive side? What do we have here? A plus.